So picking up on chapter 9, you hopefully took an opportunity to practice the first couple of things that we've lectured on so far, and now we're going to finish up chapter 9. So we have millions of different combinations of over 90 elements. All of the compounds we have in the world are always made up of elements, but we have millions of different combinations. And we do have ways to name them. We just talked about ways to name our compounds, but we also have something that's called a common name, which often refers to a historical usage before we had a naming set of rules. So some examples are baking soda, washing soda, and this tells you what you're doing. You're baking with it, you're washing with it. So often we use those, especially in the grocery store. Baking soda is sodium bicarbonate, but you don't go and buy sodium bicarbonate at Walmart. However, if you were talking to a scientist, baking soda and sodium bicarbonate are the same thing. So the problem with common names is we don't actually know anything about the molecular composition without that. When I hear the word sodium bicarbonate, I know that this is sodium and this is bicarbonate. Baking soda, on the other hand, I don't know what baking soda specifically refers to. And to be honest, I don't know what washing soda's formula is because I don't know anything about washing soda. So the monomer approach is to use the systematic set of rules. We call this IUPAC, and it's different for ionic and covalent compounds, which we just talked about. The one thing they have in common is that you're always going to change the ending of the element to IDE. So that's the only thing that they have in common. Otherwise, you treat ionic and covalent compounds differently, which you just practiced, and hopefully feel a little bit more confident in naming ionic and covalent compounds. So let's talk about chemical equations. Chemical equations are representations of chemical reactions using symbols. There are some things that are always constant. Reactants, what's reacting, is always on the left. The products, what's being produced, is always on the right. And the arrow indicates change or direction. So when we read the word arrow, we think of yields. So reactants yields products. And it's always going to be in this way, left to right, because that's how we read, is left to right. So those are the three things they always have in common: reactants, an arrow, and products. So when we use the chemical symbols and formulas for each reactant and product, we have to do something specific, which is called balancing. We need to make sure the equation is always balanced. The reason why it has to be balanced is there is a law of conservation of mass, meaning we cannot create nor destroy matter. It can be converted, but it has to be conserved. So if I have 4 carbons on the left, I need 4 carbons on the right. All elements on the reactant side should also be on the product side, and there has to be an equal number of atoms of each element on the reactant side as the product, because the arrow also represents an equal sign. So when I think of an arrow, I think equal. The left must equal the right. It's like algebra in a way. So here's an example of an unbalanced equation. I have 1 carbon, so that's good. I have 4 hydrogens, but I only have 2 hydrogens on the right, because the 4 tells me there are 4 hydrogens, the 2 tells me there are 2 hydrogens. So my hydrogens are not balanced. As far as oxygens, I have 2 on the left, and then I have 1, 2, 3 on the right. So my oxygens are also not balanced. And we're going to practice balancing equations on our next practice video. But to make it balanced, you can see here, now I have 1 carbon, 4 hydrogens, and now I have 2 oxygens, which means I have 2 of these times 2 of those, because each oxygen is bound to each other, but I have 2 separate oxygen molecules, which gives me 1, 2, 3, 4 overall. When I look at carbon, we knew carbon was balanced before. I still have 2 with my carbon dioxide, but when I put a 2 in front of the water, this means I have 2 separate water molecules, which means I have 4 hydrogens and 2 oxygens, which then balances out my formula. But we're going to practice this, so make sure you go through and you practice. There are some things I want to remind you of, that carbon by itself means 1 carbon atom, oxygen by itself is 1 oxygen atom, O2 is actually 2 oxygen atoms, CO is 1 of each, CO2 is 1 carbon with 2 oxygens. And when I write, this is called a coefficient. When I use a coefficient, it means I have 3 CO3, 3 carbon dioxide molecules. So I have 1, 2, 3 carbons, 1, 2, 3, 4, 5, 6 oxygens. So coefficients and subscripts are different. And when you watch the video, I'm going to tell you that you specifically can only change the coefficients. You will never, ever, 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 ever change the subscripts. All right, last slide is types of chemical reactions. These are how we classify them based on what's happening. So redox equations are also like oxidation reduction. This is like its combination name, like Brangelina, when Brad Pitt and Angelina Jolie were a thing. So we call them redox. This is where you have a reaction in which electrons are transferred from one atom to another. Okay, so they're being transferred. A combination reaction is a synthesis, so sometimes these words are used interchangeably, in which 2 or more substances combine to form a single compound. So this would be A plus B makes AB. Decomposition is the opposite. It's a compound being broken down into elements, something simpler or both, and it's the opposite. A replacement reaction is going to be an atom or a polyatomic, which is many ions, being replaced by a different atom or polyatomic. And we have 2 different kinds. We're going to have a single replacement, and it's kind of like changing dance partners. So A and B are dancing, and then C comes along and cuts in, and now A and C are dancing, and B is by itself. A double is where we have 2 dancing partners, and they're going to swap. A and B are dancing, C and D are dancing, and then they're going to swap partners. A and D are going to dance, and B and C are going to dance. The last one is an ion exchange. This is where ions of one compound, so think positive or negative, interact with ions of another to specifically form a precipitate, a gas, or water. The precipitate is a solid. Okay? And we're going to practice identifying the types of reactions based on the ones we're balancing in the problem before. So make sure you go ahead and finish up those practice problems that we're going to do some, then you're going to practice some on your own before you submit it to hopefully give you a chance to establish confidence in balancing and identifying chemical reactions before the test.